All right, so welcome to day 6 video. You got page 38 and 39 for homework that's due tomorrow at 5 a.m. Make sure to be working on your problem set, which is due on the 22nd, Thursday the 22nd. Okay, good idea is to go through, do that problem set early, and maybe stop into a Google Meet and get any questions answered on ones that you are having difficulty on. Okay, so we got a warm up. You can put this in Wednesday's box in the warm up. As soon as I'm done talking here, you can hit pause, take a second to try each of the warm up ones, and then hit play to check your answers. So you can go ahead and pause now and restart it once you have your answers for the warm up. All right, so point of concurrency means where they all cross. So when your angle bisectors all cross, they cross at the incenter. And a little phrase to help remember that, a big insect. So AB for a big, think angle bisector, and then the in for incenter. The incenter is the circle whose center, where the circle is centered that hits all of the sides of the triangle. Our point of concurrency for the perpendicular bisectors, that is the circumcenter. And the phrase to remember that is peanut butter chocolate chip. So the PB for perpendicular bisector and the chocolate chip helps you remember the two C's for circumcenter. And that'll come into play with today's lesson because there's another one that starts with a C. So the double C helps you remember circumcenter. Now, angle bisectors are always drawn inside the triangle, so the incenter will always be located within the triangle. But the perpendicular bisectors, the circumcenter changes depending on what type of triangle. The acute triangle, it was inside. The right triangle, it was on the triangle. And the obtuse triangle, it was outside the triangle. So the first two was just reconstructing each of our points of concurrency. So you had to do 3 angle bisectors and see where they cross to give you the incenter. And then we wanted to put our point at the incenter and put your pencil on the side of the triangle and then draw on that circle to show that it just barely hits each of them. And that comes back to our fact that point on angle bisector implies equidistant from the sides. And here's your construction of the 3 perpendicular bisectors. Extend them long enough so you can see where they intersect. Notice in this obtuse one that they intersect outside the triangle. And then you wanted to draw the circle that goes through each of the vertices that circumscribes the triangle. So put your point on the circumcenter, put your pencil on one of the vertices, and draw the circle, and notice how it goes through each of the vertices. All right, so we have angle bisectors here. They told us AE and CD were angle bisectors. So that's where those angles marked with 1 mark and 2 marks come from. Well, notice they are meeting at point G. So G must be the incenter. Well, if G is the incenter, that means that BG must also be an angle bisector because it's also meeting at G. If BG is an angle bisector, that means the angle ABG and angle CBG except, sorry, they called it DBG and EBG, would end up being the same. Next one, they told us we have an incenter, so we want to think angle bisectors. So based on the angles that we have, notice the arrows there pointing where they go. Because of the angle bisector, we know we have 2 congruent angles, so we can set those equal to each other. Solve for x. And then the big angle CAB is just the 2 expressions that they had added together, and that's our angle addition postulate. Sub in the 2, and that's where you get the 64 from. All right, here they told us the circumcenter. Circumcenter comes from the perpendicular bisectors. So notice I put each of the markings to show that they are congruent because the perpendicular bisector goes through the midpoint and it does so at a right angle. And notice we have the boxes there for the right angles as well. So we got all that information just from it being a perpendicular bisector. So we had AG as 3x minus y. Then we had GB as 13. We have AE as 5x minus y. And CE is y plus 11. Well, the 1 markers, set them equal to each other. That's the equation on the right. The 3 markers, set them equal to each other. That's the 3x minus y equals 13. Well, in this one here, we got to get it in elimination form. Put the x and y on same side, the constant on the right. And then over here, we'll write them underneath one another. And I chose to eliminate the y's, so I multiplied the top by -2, so that we would get 2 and -2 for the y's. Add them together, solve for the x's, you get 15. And then they also wanted us to find y, so put that 15 back into one of the equations to get that y is 32. All right, so we're going to be on packet page 34 today. There are 2 more points of concurrency that we're going to work on finding. We will need our compass and our straight edge, so if you could have that out as well. So we're going to construct the medians for each of these from each vertex. So the median connects to the midpoint on the other side. To find out the midpoint, we need to do our perpendicular bisector of each side. So I'm going to start with BC. Perpendicular bisector, you have to be over halfway. We'll do our swoop up and swoop down. And then we'll flip-flop it. Put your point on the other vertex. We'll swoop up and swoop down with that same arc. Then we're going to connect those 2 intersection points. And then where that segment crosses BC, that's our midpoint. So that's our midpoint right there. And let's wait. It might be a little less messy to wait, and we'll just draw in all the medians at the end. All right, so we need to next do the perpendicular bisector on another side. I'm going to do it on AC next. Put your point on a vertex. Make sure you're over halfway. Now these pictures are going to get messy. So when you do your second arc, try and keep close track of where that intersection is occurring. So I'm swooping down, there's one intersection, swooping up, there's the other intersection. So I'm going to draw a line through my 2 intersections. And where that line crosses AC, that's our midpoint. So I'm going to put a dot there just to identify our midpoint. Well, we have one more that we have to bisect. Put your point on the vertex, make sure you're over halfway. Swoop it up and swoop it down. Then we're going to reverse it. Swoop it up, swoop it down, which will give you your 2 intersection points. We'll connect those intersection points. And where that hits AB, that is our midpoint. All right, so we haven't actually done the medians yet. The medians go from each vertex to the midpoint on the opposite side. So I'm going to do like a funky line just so it's easier to see. You just do it with your straight edge. So there's one median. There's my median from B. There's my median from A. And there's my median from C. Notice they all meet at a point. They're all meeting right here. So that is considered the point of concurrency for the angle bisector. Once you're good with that, going down to the bottom, the centroid is the name of the point of concurrency for the medians. You can fill that on the gray box there. So the phrase that I usually use for that, now I'm realizing as I say this, we did not have dance marathon last year, but usually for dance marathon, there's the MCs. So MC, think median centroid. Okay, median gives us the centroid, MC. Well, the next part wants us to use the compass and measure the small part of one median and see how it compares to the larger part. So let's take our compass and I'm going to set it to the small part here. Okay, so that's the small part of our median. Notice the median is getting split into a big part and a small part. Well, let's see how many of those fit here. Well, oops. There's one, and then there's two. So two of the small parts fit into the big part. So a conclusion that we can make is that the larger part is twice the smaller part. So because the larger is twice the smaller, that breaks each median into a 1-to-2 ratio. So we say 1-to-2 because it could be, say, 5 and 10, and 5/10 reduces to 1/2. It could be 6 and 12, that reduces to 1/2. So it's not necessarily 1 and 2, but it's 1 and 2 multiplied by the same thing. And then we want to think about, could this occur outside the triangle? Well, when you draw your medians, the one that you would have to consider being outside the triangle or on the triangle is your obtuse and your right. Well, let's eyeball where each of our midpoints are. Okay, and we're just eyeballing where they are. Then connect them from the vertex. Notice even in the obtuse triangle, it does not change from being on the inside. Where we saw with the perpendicular bisector one, acute was on the inside, obtuse was on the outside, and the right triangle it was on. This is kind of like the angle bisector one. The centroid is always inside. So we would say, could it be on or outside the triangle? And we'll say no, since the median is always completely inside the triangle. So that's the centroid, which comes from the medians crossing and the things that we know about it. The other one we're going to look at today is our altitudes and find their point of concurrency. So the altitude forms a right angle with the opposite side. So in other words, it's perpendicular to the opposite side. So we need to do our construction of a perpendicular line with a point that is not on the line. So we're first going to do our one from A. So let's put our point on A, and we need to open our compass up so that it can do an arc that will hit the line twice. Now, if you find when you do your arc that it goes beyond where BC is, just use your straight edge to extend BC so that you get the intersection. All right, so we want to now use those intersection points to do our perpendicular bisector construction. So we're going to put our point on the intersection point, and we just need to make sure we're over halfway to the other intersection point. We're going to swoop it up and swoop it down. And then we'll go to our other intersection point. We're going to swoop it up and swoop it down. Oops, that was the pen. I wanted the line. So then we'll connect our intersection points. And it should automatically go through our vertex. So what this just created, it created a right angle right there with CB. Okay, so that was one altitude. We've got to do two more. So maybe we'll do our altitude from C. So let's put our point on C. And we've got to make an arc that hits the opposite side in two spots. Okay, again, if you need to extend line AB, you can do that. And then we're going to put point on the intersection. And just make sure you're open over halfway of the side. Swoop it up and swoop it down. And then we're going to flip-flop it. So put your point on the intersection. Swoop it up and swoop it down. Now notice I missed my intersection. I didn't go far enough on my other one. So sometimes that happens. You just have to go back. Just finish drawing your arc. Well, we now have our two intersection points. So we'll connect those, and we want to extend it all the way through to our vertex. And so what we've just created is we've created this, which forms a right angle with the opposite side. So we're getting really messy here, but we still got one more to go. We've got to do it from B now. So we want to put our point on B. And we need to extend it and do an arc that will hit the opposite side twice. Put your point on the intersection. Make sure your compass is over halfway. Swoop it up and swoop it down. Now it's starting to become a huge mess, so kind of try and keep an eye on when you go to do your second arc where those intersections are occurring, because it definitely gets tricky. So I have an intersection there, and you can kind of follow the arcs to see where they cross. It looks like my other intersection is there, and then it connects through to point B. So we just constructed a line that was perpendicular to the opposite side. And notice they are meeting all at one point. That is our point of concurrency for the altitude. If we go down to the bottom, the name of that point of concurrency is the orthocenter. And the phrase to help remember that, it's fall. You can go apple picking. So think apple orchard. AO. So the altitude gives us the orthocenter. That's a way to help remember it. So do you think this could be located on or outside the triangle? Well, we had an acute triangle here. So we know the acute one is happening inside. let's just sketch ourselves a right triangle and an obtuse triangle, and we'll see. And we're just gonna kind of eyeball it. So from here, if we want to form a right angle with the other side, it would be about there. From here, if we want to form a right angle with the opposite side, it's just right there because it is a right triangle. And from here, it would just be right there. So there's our orthocenter. It's right on the triangle. For this one here, if we started here and wanted to form a line that's perpendicular to the opposite side, what you have to do is you have to imagine it gets extended and then it gets dropped straight down. And that's our right angle there. Well, from here, similar idea. If we want to form a right angle with that, it would have to be something like that. And then our last one would be a right angle there. If we extend it, notice it meets up outside the triangle. So do you think it could be located on or outside the triangle? We could say yes if right or obtuse. And what you have on the next page is just a formal construction showing you the obtuse one and then the right triangle one. Okay, we just eyeballed it, but that's the actual construction showing that the point of concurrency, that orthocenter, is outside. So let's kind of organize what we've learned about the location of our points of concurrency. The incenter from the angle bisectors and the centroid from the medians always happen inside. But the perpendicular bisector, which forms the circumcenter, and the altitudes, which give us the orthocenter, could change locations. So the way I organize it in my head is any of the ones that involve a right angle. So the perpendicular bisector makes a right angle, and so does the altitude. So the right angle ones are the ones that switch position. If it's not one of the right angle ones, so if it's not altitude or perpendicular bisector, then it's just always inside. All right, let's go to the bottom of page 36. G is the centroid. So the fact that G is the centroid tells us those must be medians that are crossing, because MC. So let's see what we know. If they're medians, medians go to the midpoint. So those two must be congruent. Those two must be congruent. Those two must be congruent. And that's all just from knowing we had a centroid, which told us medians. Well, they tell us that BE is 9. When you have to label something going over multiple parts, it's a lot of times helpful to do a bracket to help label it. Well, we want BG and GE. Those are our two parts of the median that we talked about, that the longer part is double the shorter part. Or in other words, they're in the ratio of 1 to 2. So if we know the entire thing and we want to find the other two parts, a common technique is let's just call them x and 2x, because we know that the longer part should be double the shorter part. And then we could just do x plus 2x equals 9. If we combine like terms, that's 3x equals 9. And if we divide by 3, we get x equals 3. Well, the question wanted to know what BG and GE are. BG was just x, so that was 3. And GE was double that, so that was just 6. Next one, where do altitudes of an obtuse triangle intersect? Well, the ones that change position are ones that involve right angles. An altitude is perpendicular with the opposite side, so it involves a right angle. So the position of the altitude's point of concurrency should change. Again, that's the orthocenter. So for the altitude, it'll be outside the triangle. But the ones that don't involve a right angle, the medians and the angle bisectors, they're always inside. So for the medians, even if it's on obtuse, it ends up inside. All right, last two for today. So we have a triangle. They tell us that we have medians. Great, let's mark up what we know. This has to be congruent to that because medians go to midpoint. This has to be congruent to that because medians go to midpoint. And we know each of those medians have to be in a 1-to-2 ratio. The long part is double the short part. Well, they tell us we have 3q minus 1 for tq, and we have x plus 1 for qm. Well, if the long part is double the short part, that means we can double the short part and set it equal to the long part. We can distribute. Let's collect our x's on the same side. We'll subtract the 2x over, giving us 2 equals x minus 1. And we'll add 1 over to give us 3 equals x. Let's check back and see what the question wanted. They wanted us to find Tm. Well, Tm, using the segment addition postulate, would be x plus 1 plus 3x minus 1. We now know x, so it's really just going to be 3 plus 1 plus 3 times 3 minus 1. Well, that's 3 plus 1 plus 9 minus 1. The 1's add to 0, so we just get 12. So our length of Tm is 12. And our last one, we've got medians. Okay, let's think about what we know. Medians go to a midpoint, so those must be congruent. These must be congruent. And those must be congruent. We also know the medians are going to meet at the centroid, that MC. The centroid will split the median into a 1-to-2 ratio. So the long parts of the median are twice the short parts. They tell us that DC is 6x plus 9. We've got that GC, the entire thing, is 10x plus 5.5. And we want to find GD. Well, if DC is double the small part, going in reverse, that means the small part should be half the big part. So we can take the 6x plus 9 and take half of it. Half of 6x is 3x. Half of 9 is 4.5. And now we've got an expression to represent GD. Well, using the segment addition postulate, 3x plus 4.5 plus 6x plus 9 is equal to 10x plus 5.5. Combine your like terms on the left, we get 9x plus 13.5 equals 10x plus 5.5. We want to collect the x's on the same side. I'm going to bring them over to the right so we can keep a positive x. That'll give us 13.5 equals x plus 5.5. We'll subtract the 5.5 over. And that'll give us that x is equal to 8. Reread the question though. They want us to find GD. GD is 3 times our 8, which was x, plus 4.5. So that means 3 times 8 is 24, so we have 24 plus 4.5. And that then just equals 28.5. So a recap of the things for today. The medians all intersect at the centroid. The centroid splits the median in a 1-to-2 ratio, so the long part is double the short part. The centroid will always occur inside the triangle. The altitudes all cross at the orthocenter. The orthocenter changes location. If it is obtuse triangle, it's outside. Right triangle, it's on the triangle. And if it's acute triangle, it's inside the triangle. That's it for this video. Have a great rest of your day.